The stars have been whispering to us since before we knew how to listen. For most of our species' brief career, those whispers were distant and patient. The slow pulse of a supernova, the steady glow of familiar constellations, the hush of galaxies too far to see. Then, once in a while, the universe speaks more directly. A bright interloper appears in the sky, and everything that seemed settled bends a little toward curiosity. On July 1st, 2025, the sky delivered one of those messages. Telescopes flagged a new visitor, moving at a speed that declared its origin. It was not bound to our sun. It had come from somewhere else. An interstellar traveler on a hyperbolic course slicing through the familiar plane of the planets. They named it 3I Atlas, the third interstellar object we have been able to catch in the act.
50 times bigger than the first interstellar object, and that means that it's somewhere between 1,000 to 100,000 times more massive than the other two interstellar objects that we've seen before.
And almost immediately, it refused to behave like anything we had a handy category for. From the first nights it was tracked, Atlas was a study in contradictions. Observatories across the globe, hundreds of them, thousands of individual observations, recorded an object that brightened and dimmed in fits and starts, that shifted color from a muted red to a vivid green, and that seemed to shed material in patterns no textbook predicted. It moved fast, tens of kilometers each second, faster than any car or rocket we could compare it to on Earth. But speed wasn't the only oddity. Its chemistry, its motion, and its sheer implied heft were stepping stones to a much bigger puzzle. How do you weigh an object you cannot hold? Astronomers do it the way detectives do, by measuring the effects. Comets and small icy bodies, when warmed by the sun, sublimate. Ice turns directly into gas and blows off the surface. That outflow acts like a tiny thruster. Over weeks and months, it nudges the body, subtly altering its path. If an object sheds a certain amount of material and doesn't noticeably change course, that implies it must be considerably massive. Apply that logic to Atlas, and the number that emerges is staggering. A conservative lower limit of roughly 33 billion tons. Translate that mass into a solid body size at typical rock densities, and you get a core at least several kilometers across. 5 kilometers as a lower bound, perhaps much larger under other assumptions. If those estimates hold, Atlas is not a pebble or even a boulder. It is a chunk of space that would dwarf the first interstellar visitor, Oumuamua, by orders of magnitude. That alone would make Atlas remarkable. The universe is generous in variety, but the surprises kept coming. Spectroscopic observations, the breaking of light into its chemical fingerprints, revealed something unusual in the gas enveloping Atlas. Carbon dioxide dominated. Water was a minority player. In many comets we know, water vapor is the main volatile. Here, CO₂ rules. Some teams reported CO₂ to water ratios far higher than typical comets. In other instruments measured concentrations, suggesting the surrounding cloud was enormous. Hundreds of thousands of kilometers in radius in some estimates. A halo extending to a scale that feels almost humanly meaningless. Nearly half the radius of the sun in some readings. When a cloud that wide glows, it changes the object's apparent size and brightness in dramatic ways. Even more confounding was the elemental signature filtered from the light. Nickel appeared in the plume, but iron, the usual partner to nickel in natural settings, was conspicuously weak or absent. On Earth and throughout cosmic chemistry, nickel and iron are forged together in stellar furnaces. and scattered by explosions. To find nickel without iron is like finding a fingerprint where a whole hand should be. In terrestrial industry, nickel without accompanying iron is the result of refining and alloying, deliberate technological processing. That does not mean we have an alien factory on our hands, but it does set the alarm bells jangling. This chemical fingerprint demands an explanation. Motion-wise, Atlas gave more reason to frown at the rulebook. Comet tails, pushed by solar radiation pressure and the stream of charged particles we call the solar wind, traditionally point away from the sun. They form the elegant, trailing plumes we sketch on paper and imagine in dreams. Atlas's tail, or what behaved like a tail, at times seemed to point the wrong way. Observers described features that extended sunward, ahead of the nucleus, rather than streaming away. Imagine watching a dog's tail twitch toward the car, rather than behind it. That isn't how things usually behave in our neighborhood. Could gas and dust dynamics account for such a reversal? Possibly. In complex interactions with magnetic fields or asymmetrical jets of material. Could something else be at play? The data are clear only in their ambiguity. Brightness fluctuations provided the next paragraph in the mystery. When Atlas first appeared in wide-field surveys, it was faint near 18th magnitude, the sort of object that requires effort to spot. Within a matter of weeks, it surged to roughly 12th magnitude, a leap that amounts to orders of magnitude in luminous output. Abrupt outbursts do happen. Comets are notoriously volatile. Pockets of subsurface ices can suddenly vent. Structural collapses can expose pristine volatiles, and tidal stresses can fragment a nucleus. But the pattern here, the timing, the energy involved, the consistency across different observatories, hinted at processes that were either unusually vigorous or fundamentally different. Then there is the orbital geometry. Interstellar visitors, in the statistical sense, should come at us from all directions. That randomness is part of their identity. Strangers caught by the sun's gravity in no predictable parade. Yet Atlas's incoming vector lies uncomfortably close to the ecliptic, the plane in which our planets orbit. Its path is almost parallel to the familiar band of planetary motion. The odds of such alignment occurring purely by chance are small. For a presently tiny sample of interstellar objects, patterns are dangerous to claim. But this one lineup is another tile in the mosaic of oddities. With every anomaly stacked against simple explanations, more speculative ideas moved from whisper to formal suggestion. Some scientists, famously Loeb among them, have urged that we broaden our hypotheses and let the data lead us where it will. Loeb proposed a measured ranking, a scale that rates how natural versus how technological an interstellar visitor might be. By his reckoning, Atlas deserves caution, not an automatic declaration of alien design, but a signal that the anomalies are non-trivial. He and others frame it as scientific prudence. Extraordinary claims require extraordinary data, and the best path forward is to gather as much of that data as possible, which is precisely what astronomers have done. Across the world and in orbit, instruments were trained on Atlas. Hubble and Webb took high-resolution looks and deep spectral peels. Ground observatories, old and new, from the Very Large Telescope in Chile to backyard arrays contributing to distributed networks, logged photometry and spectra. Survey telescopes like TESS and ATLAS themselves provided wide-angle monitoring. Each facility offered a different vantage, a different wavelength, a different temporal sampling, a different slice of the object's behavior. From this confluence emerged the minimum mass estimate, the chemical oddities, the tail anomalies, and the timing of brightening episodes. Science, in its healthiest form, is a patient detective story. Each clue suggests new hypotheses. Each hypothesis suggests new measurements, and some measurements were scheduled to be decisive. On October 3rd, 2025, Atlas skimmed nearer to Mars than to many other planets. That near pass offered a rare opportunity. Instruments orbiting Mars, most notably the Mars Reconnaissance Orbiter's high-resolution camera, could image Atlas from a vantage point distinct from Earth. At some 30 kilometers per pixel, those images promised constraints on the object's size that would be impossible to achieve from Earth itself. Would the brightest pixel saturate and imply an enormous central engine? Would it resolve a compact nucleus surrounded by an extended coma? Those images were the kind of test that turned speculation into stronger inference. A few weeks later, on October 29th, Atlas approached Perihelion, its closest point to the Sun as seen from our system. From Earth's perspective, that moment would pass behind the solar glare, but other assets and solar observing platforms might catch signatures. Such proximity is a stress test. The Sun's heat, wind, and tides test an object's structural integrity and volatile inventory in the raw. The way Atlas responded, if it fragmented, if its plume intensified, if its spectral signatures changed, would speak volumes about composition and structure. And the interrogation did not end there. On March 16th, 2026, Atlas was predicted to loop back near Jupiter. By that time, Jupiter-bound instruments like Juno might be in position to collect additional data, imaging it from a remote but useful angle. If we had to throttle our ambitions, we would have preferred a probe that could reach out and touch Atlas, but even these opportunistic flybys offer a level of constraint that no single telescope can match. Through the months of observation, several plausible natural scenarios competed for attention. One hypothesis suggests that Atlas is a fragment of a larger body, born around a star with a chemistry different from our own. A CO₂-rich world that produced a CO₂-dominated cometary mantle. Another posits that Atlas has an uncommon internal structure that leads to episodic, sunward-directed jets that temporarily invert the expected tail geometry. A third suggests electromagnetic interactions between the solar wind and charged particles in Atlas's halo may create unusual morphology. Each of these is physically possible. Each would require specific, testable signatures. The problem is not that nature's explanations are impossible. It is that there are so many moving parts and so many odd readings that the natural solutions become contrived in turn. And then, there is the possibility that will not be ignored in public imagination. Could Atlas be technological? That word must be used carefully. It does not require arms, antennas, or a radio calling our planet. It could mean simply that the object was acted upon by intelligent processes at some earlier time, shaped, refined, assembled, or otherwise produced in ways that leave chemical and structural traces. The nickel without iron hint is the most pointed of these traces. On Earth, nickel alloys without iron are the product of metallurgy. In interstellar chemistry, such separation is not easily explained. If technology is the cause, what form could it take? A derelict spacecraft? A mining fragment?
The first trillionaire there will ever be is the person who exploits the natural resources on asteroids.
A swath of waste material?
The obvious solution is to clean up that space junk, but how?
An engineered probe? Each picture is staggering in its implications, and each is difficult to prove from spectra alone. If there is a human dimension borrowed from novels, it is this. The allure of the unknown makes us debate in public what once would have been private speculation. Scientists, wary of premature claims, nevertheless must answer the question the public asks plainly. Could it be aliens? The appropriate answer is not a brusque dismissal, but a careful, evidence-rooted explanation. We have anomalies that merit investigation, and the technological hypothesis is one among several to be tested.
It goes way out. I mean, it's out there beyond the orbit of Neptune even.
Yep.
Wow, okay. And so its period, it will not return again for what? We saw about 22,000 years.
The history of science favors bold questions but demands rigorous methodology. We should neither be naively sanguine nor reflexively dogmatic. Data, more and better data, is the path forward. Consider, too, what Atlas does to our cosmic self-image. If this object were natural, it expands our appreciation of the diversity of planetary materials and dynamical histories across the galaxy. If it were technological, it humbles us to a degree that might nudge culture and philosophy in new directions.
Now, how do we know that? It's basically, we see how much material is evaporating from the surface of the object in the direction of the sun. And that tells us how much push the object could get.
Either outcome is profound. Either way, Atlas is an invitation to watch, to measure, and to be surprised. For now, the best stories are the patient ones. Months of collected light, of spectra and images, of models run and rerun. These are the ration of the true detective, the scientist. We will see whether the Mars images constrain size to the lower bound, or whether later flybys push our estimates upward. We will learn if the nickel signature tightens into a pattern that demands metallurgy, or if calibration and alternative chemistry show a different truth. We will see whether the Sunward features are stable and replicable, or transient quirks that yield to standard plasma physics. Each answer may close a chapter. Each may open 3 more. Atlas reminds us of our mixed status in the cosmos. Intelligent and small, technically capable, but largely observational, curious, but not omniscient. We stare into the gulf, and sometimes the gulf stares back, furnishing puzzles that require patience to unravel. The narrative of discovery is rarely a straight line. It meanders, accumulates detours, and rewards the stubborn. So we track, we model, we debate with the necessary temper of science, skeptical, curious, and joyful in the chase. Whether Atlas turns out to be a gargantuan fragment, a product of exotic chemistry, or a trace of intelligence from a distant world, it enlarges our imagination. It teaches us how little we truly know about the contents and the economy of interstellar space. It pushes the instruments we build, the algorithms we write, and the collaborations we forge. We must also ask the statistical question: how common should things like Atlas be? If interstellar objects are fragments flung from planetary systems by dynamic interactions, models suggest a distribution skewed toward smaller bodies. That is to say, for every Atlas-sized behemoth, there should be a multitude of small, football field-sized interlopers. Yet our observations have so far found only a handful of interstellar visitors, a few pebbles among the cosmic traffic. Why the imbalance? Are our detectors biased toward the bright giants? Have we been fortunate to stumble on rare objects? Or is our model of interstellar debris flawed? The Rubin Observatory and other next-generation surveys promise to fill in the statistical blanks, turning the anecdotal into population-level facts. Until then, the rarity of Atlas invites both humility and skepticism. One of the virtues of the Atlas case is how it forces a global response. When scientific puzzles scale beyond local facilities, the community responds with everything it has: space telescopes, planetary orbiters, ground arrays, radio dishes, and theoretical groups modeling scenarios. Scientists write papers, sharing open data where possible, and craft models that are aggressively tested by the next observing campaign. In that sense, Atlas has been a success, a live experiment in international astronomy, with citizen observers often contributing the earliest confirmations. The democratization of observation matters here. The sky is big, but eyes are many. When the Mars images come down and when Jupiter watches again, we will be ready. The data will not be poetic. It will be numbers and spectra and pixels. But from those sterile units will spring new narratives about origins, materials, and perhaps agency beyond Earth. We will write papers, argue in journals, and, if the evidence requires it, rewrite textbooks. In the meantime, we can do the noblest human thing this discovery invites. We can be astonished and disciplined at once. 3i Atlas moves through our system like a slow, deliberate question. It does not answer by itself. It offers clues, contradictions, and spectacle. If there is a moral to this unfolding mystery, it is simple and luminous. The universe still surprises us, and our finest response is to watch, to measure, and to let the light, in all its messy, beautiful complexity, teach us anew. Join us twice a week on the front lines of cosmic exploration. Hit subscribe and ring the bell so you never miss the latest breakthroughs that could reshape our understanding of the universe. And if you're ready to explore another mind-blowing discovery from the cutting edge of space science, dive into our next episode and save to watch later. Thank you.